Good morning, everyone. So, as he said, my name is Dávid Halász, and I'm going to talk about smuggling, sockets, proxying with Rack and Ruby. Sorry. I'm clicking Nadia's slides by accident. So this is my very first time in Kiev and Ukraine. It's really nice. I hope I got the colors. Usually when rock stars and showmen come to a country, they try to charm everyone by saying something on your language. Ja to robiť nebudem, lebo váš jazyk nepoznám. Prepáčte. So it's a really nice place. I walked around a little and I found this sign. And I like to live dangerously. And not by just putting a lighter before a picture, but I'm going to just start up a live demo, which will boot up a container. You will understand it at the end of the talk, but it needs like up to 10 minutes to download a container and spin it up and run everything. So let's start it. And let's go back to the talk. So I'm Hungarian, born in Slovakia, living in the Czech Republic. It's pretty complicated. That's why I was speaking something similar than you could understand. I live in a town called Brno, which is famous for beer, MotoGP, and we had in the 19th century a really famous genetic experiment. Not him. So in the 19th century, Gregor Johann Mendel, the father of genetics, did some experiment with peas, which is not Frankenstein. So I work for a company called Red Hat on a project called ManageIQ, which is for cloud management. You have a cloud, we can manage it. Of course, it might be more interesting for you that it's written in Rails and it has a huge code base. We support a lot of platforms, and what just happened? Okay, it's back. It wasn't me. So the stuff I used to work on are called remote desktop sessions. Remote desktop sessions are, if you ever used Windows, you can connect to another desktop by entering some credentials. In a company where you do Linux, it's kind of hard to get a machine like this for demoing. And I don't know the password, so whatever. You get the idea. So more specifically, I'm working on in-browser remote consoles, which are basically browsers running a remote desktop session in an HTML canvas, surprisingly. And it basically works like you have a button on a VM summary page, a virtual machine summary page. You click on VM console, and it opens you a window where you can remotely access your virtual desktop. The architecture is you have your VM and your browser. The VM runs on a hypervisor server. This server exposes you a VNC port. You can actually do this in a VirtualBox or any virtualization technology on your computer. So you can expose a remote desktop server. The browser doesn't really understand VNC, and you need some bidirectional communication. The closest thing the browser supports is WebSockets. And between WebSockets and VNC, you need something in the middle that would bridge those two languages. Let's call it proxy. So here we are at the first chapter, the proxy. If we look closer at the proxy, you will see some scary words inside. The proxy consists of networking, blocking, non-blocking I/O, concurrency, and all those scary things Ruby people are really freaked out of. I'm going to demystify everything, no worries. So from another angle, the proxy On one side, you have an endpoint for WebSocket. On the other side, you have an endpoint for VNC. And you read from the WebSocket and write to the VNC. And you read from the VNC and write to the WebSocket. And you do translation between the two languages. It's pretty simple. When I talk about endpoints, what are these endpoints? So if we uncover them, you will see that they are sockets. This joke works only in Europe, so sorry for UK and US and Australian people. You are laughing, but it actually didn't work in Australia. I had to explain. So sockets in Ruby are implemented like this. So you can open a connection to rubyc.eu on port 80. Does anyone know what's port 80? Yeah, it's HTTP. So you write your request, you read a response, you get back a response. This is a request response protocol HTTP. Actually, I'm reading HTTP, so it's forwarding me to HTTPS, so it's a good thing, rubyc.eu. Well done. And if you look at these methods, write, read, close, what other abstraction other than sockets come to your mind? Yes, sockets are basically files, but for networking. With a little twist, I'm going to explain. So if you are trying to write to a socket, you are not actually writing to the network directly, you write to the buffer, and the operating system offloads this buffer when there is time, there is space on the network card to the network. So your data comes into the buffer, and whenever your network card isn't busy, it takes out the data, forms packets, and sends to the network card. Do you know what happens when the buffer is full? No, you wait. This is why it's called blocking I/O. So when the buffer is full, you're trying to wait, the operating system basically blocks your connection, and you cannot write into the socket. You have to wait until it's offloaded. And this is not a nice thing, because your thread is actually being busy with doing nothing. I could explain you the reading, but I'm not going to do that. And if you would like to see an example, so here we have two sockets, and because we do blocking operations, we have to implement threads. So here we have reading, I do some translation from WebSocket to VNC, and write to the other socket. And because the buffer can get full, this has to be looped. Because the transmission is unending, this has to be looped. And because this can be blocking, it has to be a thread, so you can do the other side. Because in any other way it wouldn't work, because it will just loop on the first one. So you have two threads, reading, writing, in an endless loop. It's not very effective, because GVL and other scary stuff. So Ruby doesn't allow you to run more than one thread at the same time, so it switches your threads, and they are not actually running concurrently. So there is a solution for this with non-blocking I/O. Basically, they are the same methods, read, write, but with a non-block suffix. So read, non-block, write, non-block. These methods aren't waiting, and under the hood, they are implemented by testing the buffer, and if the buffer is full, they just throw you an error, E would block or E again, depending on if it would block or you wrote something, but not everything went through. And the readiness testing, where you actually wait, we actually blocked, is extracted out to a separate system call. Using this, you can have a single loop, a single endless loop to handle any sockets. The readiness testing is done by select. So you pass the select system call an array of reads, writes, and errors. You're testing for the sockets being ready for reading, writing, and if they have any error, and some timeout where you wait for some time until you block. So basically it got extracted out, the waiting got extracted out, and you can give some maximum amount of time you wait. And basically, it sleeps until anything becomes ready, something becomes ready. And if you set a 0 timeout, then it sleeps for eternity or when something becomes ready. An example with this is here. So I initialize an array of sockets with an event loop in a thread. There is a method for registering a socket, so you push into that array new stuff. And there is an event loop, which is an endless loop that checks for readiness for reading. So we do IO select sockets, which gives us a to-read array. And that to-read array will have all the sockets that are ready for reading, and they wouldn't block. We can go through this array and read the data without waiting or just sleep. This is really nice if you do one direction readings, transmission. So if you're reading from one side and then you do something with it. The problem comes when you're trying to work with dependencies. So you're trying to read from A and write to B. For that, you need to pair the sockets. Let's say socket A is mapped to socket B with this method for translation, and socket B is mapped to socket A with another method translating the two languages, WebSocket and VNC. You have to do an endless loop again. We select the sockets keys for readiness, and we wait 1 second, and we iterate through all the readable sockets. We get the other endpoint and the translation method. If the other part isn't writable, then we skip the loop. And then we do the transmission, read non-block, translate, and write non-block. So this is how we do it naively in non-blocking way. This has a problem, because what if socket A is ready for reading, but socket B isn't ready for writing? So you get into this IO select, and the reads, I hope it's visible. Is it? Yeah, so the reads array will only have socket A. The writes array will be empty because nothing is ready for writing. You iterate to the reads array, and here in this read, it will be socket A. The write will be socket B, and writes is empty, and it doesn't include socket B. So you get back to this point. You call the IO select, then you iterate again, then you jump out again, then you call IO select again. You don't wait because something is ready for reading. Iterate again, jump out, and your CPU feels like this. It eats up 100% of your CPU, even if you're doing as IO select, because IO select returns immediately, and it's not very effective. This is really bad, and we had this code in production for 2 years. So I was looking into alternative solutions, like not using Ruby or quitting my job. Using threads with blocking I/O is a no-go because GVL. Using a library for asynchronous I/O. So Celluloid and Event Machine use some magic that turns your code into non-blocking automatically. The problem with them is that they aren't really compatible with Postgres, which we are using in an async manner. So it's just crashing when we try to start it. And async is a really nice gem with fibers and resuming fibers and exception handling. You really should try it out. I would write the whole solution right now in async, but that time it wasn't really existing, or it was in early phase, and if I would do it, this talk would never exist. And I was also looking into autofibers, which are basically fibers, really lightweight threads, that return the context when you would block. So if you would put a sleep into your autofiber, the fiber calling mechanism will just quit and you could run something useful. It's very similar how Crystal implements spawns, if you know them, fibers, basically. So I was really excited about autofibers, and I looked them how it would look like if they would exist. So here we have the two sockets, WebSocket and VNC. We have a fibers array, and similar to the thread, we create two loops for reading and writing in a blocking way, and wrap them into auto fibers, which are similar to threads but not, and run this. I'm not sure about the syntax, but we basically iterate through all the fibers in an endless loop, and whatever is ready, it will be called by magic. So it's a magic that translates your blocking I/O into non-blocking I/O. A very similar thing happens in Go if you ever used Go routines. The Go runtime actually schedules your stuff, and using some magic, it transforms your blocking I/O into non-blocking in an invisible way. Unfortunately, auto fibers aren't really existing yet. So I'm waiting for it, Matt. I'm really waiting for it. Until then, we had to come up with something else, and we found... I will let that guy take the picture. So we came up with the idea of bouncing select. And it's about the arrays where we have the sockets to read and to write are mutable. So whenever a socket is ready for reading or writing, we remove it from this socket. We bounce it out. And after the transmission, as you see it here, sorry for the others, you see it there, we put it back after a successful transmission. So let's say when we have socket A ready for reading and socket B not ready for writing, we have the two arrays like this. But after the bounce out, we remove it from to read and to write, and this will be empty. And when we iterate through, this socket B will not be in the array, so we jump out. But here, to read is empty because it's already ready for reading, and we don't need to test it again. So here, our CPU can finally rest a little. So this is how we bridged out the spin lock and made it a little more effective. This is still not ideal because I/O select is slow for a lot of connections. So if you try to test 2,000 connections, you have to copy all your 2,000 connections to the kernel's memory space and then test it, then copy back the result. And it's not very effective if you have thousands or tens of thousands of connections. And I was looking into alternatives, and I found epoll, which is a Linux-only system call. Sorry for Mac users. And our stuff runs on Linux, so I was happy about it. So it's much higher performance because the copying and the waiting part is separate. So you basically register your socket for readiness before you wait for it. So you register once and wait multiple times, so it's split up faster. It's available on Linux only. There is a similar implementation on BSD called KQ, and my solution was to fall back if epoll isn't implemented to select. It partially can implement the bouncing select with the epoll one-shot flag. Basically, if this flag is set and your socket is ready, it gets automatically removed from the internal structure, and you have to re-register it. So these two operations are done for free for you if you are using epoll one-shot. You have to re-register it out again, but that's not so hard. So it's written in C because there was no library that implemented epoll one-shot. There were some libraries bindings for Ruby for epoll, but none of them were implementing one-shot, so I wrote it on my own. So there is a registering function which sets the flags, epoll in, epoll out, reading, writing, and one-shot, adds the socket, and then we have a select call which actually does epoll wait, and the results are copied back to a Ruby array where you can use the code again in Ruby. This works really well in Linux, and as I said, we fall back to I/O select. If you would like to do an implementation for Mac or BSD using KQ, here is the URL for the proxy. I would be happy to merge it. The problem is that EPOL does the memory allocation for you for free, and you don't have to care about it. KQ doesn't do it, so good luck with Walgrind and memory leaks. I gave it up after a month. So this is the proxy part. Second part is WebSockets. Does anyone know what WebSockets are? So using HTTP for bidirectional data transfer instead of classic request response ping pong after an HTTP handshake. So you have your browser and web server. You send a request with get connection upgrade and upgrade to WebSocket. You ask the server that, hey man, do you speak WebSocket? And your server says, yeah, sure, let's talk in WebSockets. And then they start speaking in WebSockets. So it's the same connection. It opens as HTTP, but it ends up as something else if they both agree. Actually, HTTP 2 is implemented in a similar way. So you upgrade from HTTP 1.1 to 2. And most of Ruby servers are implemented in REC. This is a really commented example from the REC website where you have to define something that returns a three-element array and responds to the call method. Here I did a lambda. And the first member of the array is the number, is the HTTP status. The second one is headers, and the third one is an array that contains the string that's rendered on the page. And then you run this middleware or server with any handler. Here I'm running with Puma. I have some highlights I forgot about. I'm really sorry. Basically, you call a function for each incoming request. So it's basically a function as a service, but no. The problem with this is that it's not really good for bidirectional connection because you would live here and, for example, Puma can handle 4 connections at the same time. You have 4 WebSocket connections with this architecture, and it's spinning all the time. You cannot have a 5th one. It's really ineffective. So the developers of REC came up with the idea of socket hijacking. The idea of hijacking is that you ask for a socket descriptor and take it out from the connection. So here I have a proxy which runs in the background. I test for we support HTTP upgrade. Then this is the socket hijack call that gives you back the socket. And after that, the server doesn't care about it. Then you can do some magic that will get you an endpoint address and port. Then open a new connection. The VNC one, the WebSocket one is this one. This is the VNC one. And we put it into the proxy. And we tell REC to move on and don't care about it. This is how we run our remote consoles. So basically this architecture. And I promised some smuggling at the beginning. So when I was implementing hijacking, but remote consoles, I was looking into this upgrade header. And I was thinking about what if we could upgrade to something else, like GET. And I was looking into the specification, and theoretically it's possible to upgrade to something else, whatever you want. So I started to be happy because instead of this architecture where you have a browser and you tunnel your connection through WebSocket, you could have a desktop client with a client proxy that tunnels your stuff through something with as HTTP and go through any firewall you know, because it's camouflaged as HTTP at the beginning, but then you actually downgrade to TCP and send through VNC packets through the HTTP connection after the handshake. And some of my colleagues were like this, and for them I told this. So a browser-based remote console client like VNC will be never as fast as your desktop client because you do 3D rendering and video playing and keyboard shortcuts and key mapping. Those things doesn't really work in browser that well. So I had a really important problem. As you know, in computer science, there are two really hard problems: off-by-one errors, cache invalidation, and naming things. So I asked my sister how to call this thing. And we came up with this, which stands for Protocol Upgrade Draw Request. And it's basically HTTP upgrade, and after the upgrade you do VNC, or you do SSH, or you do whatever you want. It's basically TCP smuggle through HTTP. And because it's not tunneled into anything, it's actually TCP sent through after the handshake, so it's smuggling, I guess. So in our architecture, where ManageIQ runs with a virtualization platform, and it's basically one web server with a Rails application, you click on a button on a VM, say native console, the browser sends a connection to the web server. The protocol isn't figured out, so it's maybe not the right language. So the web servers say, sure, go ahead. Here is the URL you can talk to. It starts with per. That triggers a browser extension. This browser extension sends you back a URL where it's listening. Then the browser can show you a URL, like, please point your favorite client to localhost 1234, which is in your computer. Then you can connect to localhost 1234, which connects to this browser plugin. The browser plugin opens a connection to the web server, which is forwarded to the proxy directly because it's one thing. Then you do the HTTP handshake, and you have your per connection. The proxy opens a VNC connection, and through this blue line, if it's visible, you have a direct connection from the VNC client to your virtual machine using only HTTP or HTTPS. I lied. Browser plugin, that isn't enough. You actually need a native binary to listen on a TCP port. So I had to do a crazy twisted architecture with a server, a plugin, a client proxy, and a front-end library, which will go away after the HTTP, the W3C people finally implement the TCP listen and the permissions API in the web standard. It's ongoing, and I expect it in 2 years. Until then, you can use the client proxy and the plugin. And I really like a front-end library, so if someone likes writing JavaScript, please contact me. The server in Ruby is super simple. You just have to implement a magic function that returns you a host and a port, and your incoming connection will be translated to that endpoint. It's really cool because it's like HTTP, so you can use routing, authentication, logging. It can be HTTPS. You can have cookies. And for now, you need the browser plugin and the binary. So based on the URL, you can route to a computer that only that person has access to, which has the URL and the name and the password in the web application, for example. It's really far from being production ready, but it works. And I know talk is cheap, so now we are getting to the demo. And until the demo runs, I have this animation. So I have a container, I have a VM running 2 containers. 5 minutes, OK. So I have a VM running 2 containers. One container is running a VNC server. Another container is running an SSH server. And those containers aren't exposed to my machine, so I don't see them. I don't think we have the time to show me that I cannot ping them, but afterwards, if you have questions or something, I can show you. So the VM is running on this address. I need to switch the displays because... OK. What happened? Yeah, it's here. Yeah, I clicked the wrong button. I'm sorry. Mirror, apply. Now it's good, right? Yeah, okay. So the VM's address is this, and I will run the server, which is just running per and having 2 URLs exposed. So if I do, no, I do 9292, I have a very simple demo. I will zoom in. Three buttons, one for starting VNC. It will ask the per server to give me a URL. This is the port. I will run a VNC client. I'm connecting to localhost this port, and it actually goes to the container. So this connection here is running through an HTTP connection to a container which isn't exposed to my machine. And before you would have any performance questions, there is no sound. In the meantime, I can show you SSH. So there is another container with, sorry, I don't want debugging. I want to copy. And so W is just for not caring about keys. It's nothing scary. So I'm connecting to the machine. I'm there in that container through SSH. And if I press this button, so I will put this here and this here. If I press this button, all the 2 connections will go down. This one as well. Thank you. Do we have space for questions?
Yeah, we have 2 minutes.
Okay, so I have some stuff from Czech Republic for anyone who has questions and some stickers.
Great. So, does anybody?
Relevant questions.
Yeah.
Yes, thank you for the good talk. Actually, the question: are you still like GIL locked? So you still use like one CPU, or actually the solution it uses 5%?
So the waiting is running in a separate thread because it's written in C. It's offloaded. So I'm not using the GVL there, but all the Ruby stuff is still in one thread. Yeah.
So, but actually, WebSockets connection, for example, it's managed to hold only one CPU manages the connections. So it's still has issues.
Well, if you are using JRuby, then no.
Yeah.
Or Truffle Ruby.
Thank you.
Anybody else? Any questions?
Benoit.
Thanks for the talk. I want to ask, what is the purpose of using HTTP instead of like native exposing ports?
Yeah, exposing ports is dangerous, and anyone can connect to that port. And you have like 65K guesses. And here you have a URL. You have unlimited guesses, and you can have authentication around it. So let's say you want to expose this connection only for a short amount of time for one person. So we have an authentication chain around it, names, passwords through HTTP. Your plugin inherits all these.
Right, and were you thinking about combining those approaches, like handling authentication via HTTP and using like APIs, exposing ports based on what you've got in your browser?
Yeah, so we work with people who don't like exposing ports.
Oh, okay.
Yep.
Thanks for the talk. Earlier, so you mentioned like because of the GVL, the thread approach was not really, you didn't like try it. But in your case, isn't it mostly IO bound, or maybe I misunderstood something there?
Yeah, it's IO bound, but after 500 connections, it dies.
Because too many threads. Or...
Yeah, the EPOL one can do like 10K more, 10K plus. I didn't go more up, but 10K was doable.
Right, and at some point select would be really slow as well. And then, yeah, okay.
Thank you, David.